Welcome to our explainer. We're going to pull back the curtain on the invisible magic that powers our entire connected world. In just the next few minutes, you'll finally get how the tech you use every single day actually works.
I mean, really think about that for a second. You say hello into your phone, and someone on the other side of the planet hears you like you're standing right next to them. How is that even possible? Well, the answer starts with understanding the single biggest challenge in all of communication.
And this quote nails it. The whole point of communication is that it's unpredictable. Your voice, a video, a text, it's all new information. If we already knew what you were going to say, why would we need to send it? So to handle all this uncertainty, this randomness, engineers use the incredible power of probability.
Okay, so how do we get that unpredictable message from you to your friend? Engineers have built this amazing system for it, and you can kind of think of it like a high-stakes relay race for your information.
The race kicks off with a source, that's you, talking. The first runner, the transmitter, grabs your message and gets it ready for the long journey. Then it passes the baton through the channel. Think of this as the open air. On the other side, the receiver catches it, figures out what it means, and delivers it to the finish line, your friend's ear. But that middle part of the race, the channel, that's where things get really tough.
But hold on, before our message can even hit the starting block, there's a huge physical problem with the signal itself that we have to deal with first.
You see, the raw electrical signal that your phone creates from your voice is called a baseband signal. It's got all the information we want to send, but it's stuck down at really low frequencies.
And here's the crazy part. To actually broadcast those low-frequency signals, you would need an antenna that is literally miles long. Yeah, good luck fitting that in your pocket. It's just completely impractical.
So since building antennas the size of skyscrapers was a non-starter, engineers came up with this incredibly clever way to disguise the signal so it could travel. They came up with a process called modulation. Now, the best way to picture this is to think of your message as a passenger. Modulation basically puts that passenger onto a super-fast airplane, a high-frequency carrier wave. This new combined signal is now perfect for zipping across long distances.
And this modulation trick is absolutely critical. It's what allows for the small, practical antennas we have in our phones. And not just that, it's also what lets thousands of different signals, radio stations, cell calls, Wi-Fi, all share the same airwaves without crashing into each other.
All right, our signal is disguised and it's airborne. But the moment it leaves the safety of the transmitter and flies out into the channel, it comes face to face with its greatest enemy. Noise. It is everywhere. The universe is just humming with random electrical energy. It's like a constant static hiss that attacks our signal the second it's out there. This noise is always trying to corrupt and distort the precious information we're trying so hard to send. So engineers have a way of measuring this fight. It's called the signal-to-noise ratio, or SNR for short. When your signal is way stronger than the background noise, you get a high SNR and a super clear call. But when the noise starts to creep up and your signal gets weaker, that SNR drops, and that's when you get static, garbled words, and dropped calls.
For well over a century, noise was just a fact of life. It messed up every analog signal, like old-school radio or TV. But then, the digital revolution came along, and it gave us the ultimate weapon to fight back.
So here's the key difference. An analog signal is like a smooth, continuous wave. Any noise that gets added to it just sticks to it permanently. You can never get it perfectly clean again. But a digital signal, it converts all that information into a simple stream of ones and zeros. And that simple language makes it unbelievably tough. The secret weapon here is a little gadget called a regenerative repeater. It catches that weak, noisy digital signal and makes a very simple choice. Okay, is this messy pulse I'm seeing closer to a 1 or is it closer to a 0? And once it decides, boom, it generates a brand new, perfect, totally noise-free copy to send down the line. It literally kills the noise at every single step. It's genius. So even with these incredible solutions for tiny antennas and killing noise, communication engineers are still locked in this constant battle against scarcity. They just never have enough of the two most important resources. It's this constant balancing act. On one hand, you have transmitted power. You can always just shout louder than the noise, right? Boost your power, boost your SNR, and get a clearer signal. But that power absolutely drains your battery and costs a ton of money. On the other hand, you have channel bandwidth. That's the slice of the airwaves you're allowed to use. It is a finite, expensive highway, and it sets a hard limit on how much data you can push through at once.
And this, right here, is the fundamental puzzle that drives all innovation in communications. Every new technology,
whether it's 5G, 6G, or whatever's next, is really just a new, more clever way of balancing this trade-off between power and bandwidth. It's a relentless race to do more with less, which leaves all